Alrighty, guys. Excuse me. We have a little bit of time before we start. Are there any questions? Okay, we'll give it a few more minutes and then we'll get started on the lecture. Alrighty, guys, let's get started. Can you hear me?
Yes.
Okay. There was a question out in the log. Do you think the book chapters can suffice for supplementary material? Yeah, I mean the expectation is that you have the textbook, and the syllabus outlines the sections that we're covering. So between the textbook and the lectures, this is all you need. There are sometimes I'll post a document or two on Canvas on some special topic that has come up, but in general, the two textbooks and the lectures, that's all the material you need. We are falling a bit behind, and I sent out an email earlier today that I pushed the homework date a few days because yeah, we're falling behind, and the material that you need to solve the homework, some of that is tonight's lecture. So I want to give you guys a chance to see this material before you start solving the homework problems. So it's been pushed a few days, and just gives you some breathing room. It also means that I'm still not quite sure when the oral exams are going to take place, but it's going to be in the second half of October. So I want to see how the material and how far we get in the material, and then I want to have some time between the end of when we go through the material and then when the period of oral exam is going to be, so we can have some time to have questions and answer sessions. Maybe some of you, or maybe some students, they want to try to do a test run on the how it will be to do an oral exam using Zoom. So I want to have time that we can do that. Okay. That being said, let's get started on tonight's material. Okay, so the goal of tonight is to define. It is to define this conditional expectation E of x given g, where x goes from omega into the real line, measurable, and g is a smaller sigma algebra. Right. X is measurable with respect to f. Remember what it means here. It means that when I look at these level sets, when I look at these sets, I get something that's inside f here. For any element x in the codomain. And so here we have a sigma algebra, and it's potentially smaller than f. And what we want to do is we want to compute the conditional expectation of a random variable given g. Okay, so we want to think of, you should think of this expectation here, the expectation of x given g, as an estimate of x given your knowledge of g, right? So what does that mean? So if you look at an example, and the example here is highly related to some of the problems in your homework. If I take two random variables, let me call them x and y, and let me make them Gaussian. Right, so I'm going to say that the are normally distributed, the jointly normally distributed. I'm going to put in the mean, and we're going to put in the variance. And the mean and the variance is listed, the means are listed in the first vector, and then in the covariance matrix, you're going to find the variance in the diagonal. And then off the diagonal is going to be where you find the covariance. So I'll put in a row here. Right, these here are the means. So I have E of X, I'll have E of Y, and this one here would be the variance covariance. So the variance covariance. So here what I'll have is I'll have E of X squared, and I'll have E of Y squared. And then after diagonal, I'll have the expectation of X times Y, the expectation of X times Y. Right? So you can see it's symmetric. So whatever is here needs to be up here as well. So we have two joint normals. Sometimes yeah, so let's have a quick look at the joint normal density. I'm not going to write it out because it's just long and messy. But let me just give you an idea about where you can find it. So this here is in the textbook that we are currently working on. This is number 2. So in here you'll find a two-dimensional density, and you can see it's a long and messy expression, which is why I don't want to write it on a piece of paper. But you can see inside here there are like sigmas. You can see there's a rho, and you can see there's some mu's, and these parameters. This is what you find in the mean variance covariance matrix, and what you find in the right. So the means are the mu's, the variance covariances are the sigmas, and the rho. And one thing, and this is the only thing that you should take away at this point from this formula, is when you see where rho is, and if you pick rho to be 0, when you pick rho to be 0 in this messy formula, you will see that the joint density becomes the product of the two individual densities. So that's important, right? So what that shows is that if rho is equal to 0, you get independence. And this is a special property that you should not expect in general, but we should know. So there are some facts. X and Y jointly normal has, so when X and Y are jointly normal, then X and Y are independent if and only if the covariance is 0. And it's very important here to understand that this is not going to work without the word jointly up here. This is just a warning. X normal, Y normal, covariance being 0. This thing here does not imply at all that X is independent of Y. You need to have the word jointly normal for this to work. So this was one fact. Another fact that we're going to be using is that if I take linear combinations of jointly normals, right. So if I have X and Y are jointly normal, I take a linear combination. Linear combinations of jointly normals are again jointly normal. Right, so in my example up here, if I take, so for example up here, if I take X and Y to be like this, I will take 7x plus 19y, this random variable, if I call it was z, then, for example, this guy and x, they are again jointly normal. So if I take linear combinations, those linear combinations, they are again within the jointly normal family.
Professor, when we say something's jointly normal, what's the difference from like when you wrote the arrow and you slashed it? What's the difference between the x and y there when it's like not jointly normal?
What does it mean when I put a cross over it?
No, I mean like what like how are x and y related when they are jointly normal and when they aren't jointly normal?
I mean, so then we go back to this formula. Right? If x and y are jointly normal, then their density has this long and messy expression. Right. If x and y are jointly normal, then their joint density has this form.
But if they aren't, they just don't have, they have some other form or like.
Then they have some other form, right? I mean, there's no, this here says that if they are, if they have the joint density, they are jointly normal. Right? And if they don't, you're not. That's,
Okay.
yeah. I said there's an example here just before it, right? This is this example here, 2.210. I'm not going to take you through all these calculations. There's some of these calculations are happening in your homework. But what it says here is that if I take normal random variables and they're uncorrelated, I can actually get them to be dependent. And so that's because down here, even though you have x and y are individually normal, they're not jointly normal. Being jointly normal is much stronger than being individually normal. And then this is what happens in this example.
So are x and y still independent?
No, independent is stronger. If you're independent, then you're also uncorrelated. Right, so we always have that x and y independent implies that the covariance between x and y is 0. Was that your question?
Yeah, I got you.
Okay. This is not, you get this. How do you do that? Well, you do that by saying that, well, the covariance between x and y, by definition, this is the expectation of x times y minus the expectation of x times the expectation of y. That's the definition sign, right? This is what we mean by covariance. But if the independent, then the expectation of a product is equal to the product of the expectations. But that's the same stuff as we have over here. Right, so that's 0. So you have independence always implies no correlation or no covariance. But you do not have the other implication. The other implication is much, much harder. So the other implication is true, as we're saying up here, is that right, it's going in this direction. That's hard. The other implication says that if you have joint normality, well, in that case, if you have no correlation, then you also have independence. Okay. being independent is much stronger in general than just being uncorrelated. Okay, so we're playing with this example here. We're trying to get at how to define this conditional expectation, and this is what we'll be doing now. So what is meant here, right? You should think of this as an estimate of your knowledge related to G. Okay, but this is pretty vague. What about in this example here? So we will have set the G to be just a sigma algebra generated by Y. Okay, so then let's look at some cases. If I am to compute the conditional expectation of X given Y, how would this translate up here? So now what we're thinking about is somebody tells us where Y is. Now what's your best estimate of X? Okay, so let's look at some extreme cases. Well, one case could be if I take rho to be to be either plus or minus 1. Then what? Well, in that case, X and Y are perfectly correlated. So if somebody tells you that Y is 17, what do you think X is?
17.
So this just means that X and Y, I mean, if I know what Y is, I know what X is. So this estimate in that case will just be Y. What about if we're in the other case? If we're in the case where rho is equal to 0. So then X and Y are what? Then they're independent.
Does it mean that the condition doesn't matter?
Yeah, and so how do we write that down?
It just equals E of X.
Yes. So here's a constant, and here is the random variable by itself. So what about in between? What about rho in between? Well, that's a good question. This is what we have to figure out. But we're not so far away from it. But maybe you can sneak peek a little bit on how would one go about doing this. The trick that I want to show you now, this is something that it's hard to underestimate the importance of this calculation that we're about to do. It has come up. This is not some random thing that I'm pulling out of the hat that this is how one can go about solving this problem. This is quite important for all kind of applications. I mean, the Gaussian distribution is very important, and this particular calculation we're about to do now, this is really an important part of being able to work with the Gaussian. So the general case, right, so now we don't have independence. So it's not clear what you should get here on the right-hand side. Okay, so here's the way to go about it. So there's a useful trick, and this is a useful trick, and it comes up often. So you don't have independence, and you would really like this thing to be, that thing you're conditioning, you would really like it to be independent. So you come up with this idea that maybe I can create a new variable, which is going to be independent of that thing I'm conditioning. So you're going to create a new variable And what you have at your disposal, are these linear combinations. Okay, so we pick a linear combination here, and the linear combination that I'm going to pick is going to be x minus rho y. Right, so you're going to define a new random variable. This y perpendicular. And now that's a linear combination. So you know this is going to be Gaussian, it's going to be jointly Gaussian with x, it's going to be jointly Gaussian with y. And if you work out what the distribution is going to be, well, the mean will be the mean of x minus rho times the mean of y. Well, x and y both have means 0. Right, that was given. We had means of 0 here in the mean vector. And then what about the variance? The variance is going to be the variance of x. Okay, so that was a 1. Then it's going to be plus the variance of the second part. So it's going to be rho squared times the variance of y, which is again a 1. And then you get minus 2 times the covariance. This is minus 2 minus 2 rho times the covariance between x and y, and that was rho squared. So you can simplify this thing here out. This is going to be 1 minus rho squared. So y perpendicular is Gaussian. It has mean 0. It has variance 1 minus rho squared. And if you want to test for independence, so this here is that's the important part. So y perpendicular is actually independent. Is independent of y. So the first thing is you note that y and y perpendicular, they are jointly normal. And again, note the word jointly here. And the reason they're jointly normal is exactly for the same reason. It's exactly for the same reason that we had here. We get 7x plus 19y. Well, this is a linear combination of jointly normal, so it will preserve the structure. And so you get that random variable and x, for example, they're jointly normal. So, okay, so here we have another linear combination of x and y. So this is going to be jointly normal with y, it's going to be jointly normal with x. And then, because of 1, the second thing to note is if I look at the covariance between y and y perpendicular, I can figure out what this is now. I can compute, this is the expectation of the product. Like they all have mean 0, so we don't have to subtract away the means over here. They all have mean 0, so here would be the expectation of y, and then times is y perpendicular. Y perpendicular, we had the formula just above. Y perpendicular is space here. So the y perpendicular, this was x minus rho y. So the expectation of xy, this was rho. Minus, then we have a constant. And then the expectation of y squared, this was 1, so this is 0. So you combine 1 and 2 to see that y perpendicular is independent of y. So the trick is if you're lacking independence, and this is something that we will often look for, the trick is to look at some linear combinations that will buy you back this independence. And now just see how this here will then solve our problem. What we'll do is we're looking to compute these conditional expectations up here. So we will look at computing the expectation of x given y. We look at computing the expectation of x given y, and what we do first is to solve for x in the equation. So we move minus rho y to the other side. So we give me y perpendicular, and then plus rho y. And I need to condition on y. So now what we want to do is we will have to have, we're still just playing around. We haven't given the formal definition here, but it seems like a conditional expectation of this sort, it should be linear. Like if I have an expectation of a linear combination, I should be able to pull constants outside, and I should be able to, the expectation of a sum should be the sum of the expectation. It should be linear. Okay, so we need to have that. So here we'll use linearity. So we'll get the expectation of y perpendicular given y. And then we'll get rho of y given y. And so then what? Now we're basically back to a combination of the two things that we had before. Like if we believe that this object should really be an estimate, so I'm telling you what y is, what do you think y perpendicular is going to be? Well, the independent
Just give y perpendicular.
should just be the expectation, yeah? And now the other one is my rho. Okay, I'm going to tell you what y is. What's your best estimate of y? I tell you y is 17. What is your expectation of y? Well, 17.
Yeah.
And now the expectation of this y perpendicular, well, we know that because we already settled on it. We already figured out that this was a 0 that's sitting in here. And so we just plug that in there. We end up with rho y. So we see here we're using a bunch of properties. Where we're using here, this one here, we wanted to have linearity. This one here will say that I use that the expectation of y perpendicular given y, that was 0. I'm using that the best estimate of y given y, and that's all equal to y. So I'm using a bunch of properties here of the conditional expectation to perform these calculations. So when I go ahead and this is what we're going to be doing next, right? And we're going to give the formal definition of this conditional expectation. And then what we want to make sure is that after that we have all the properties that we just used.
How did we know that expectation of y perpendicular given y was 0 again?
Well, the first equality sign here is you're saying that I'm trying to so the intuition is we're trying to estimate something that is independent.
Right, and it doesn't matter, so it just becomes the regular.
But the expectation of y perpendicular is 0, because the expectation of x is 0 and the expectation of y is 0. Y perpendicular is just a linear.
Oh, okay. I see.
Right, that's the 0 you have sitting here.
Right.
Okay. So all this here just serves to give you it just serves to give you like a basic example of something that is much more general. And so here comes the general definition. And the general definition is not particularly pleasing on the eye, but that is the one. Okay, so we're going to do a definition now. So a random variable is going to be denoted by E of x given G. And it's going to go from omega to R. A random variable with this structure is called a conditional expectation of x given G if. So then there are two statements coming out now. So the first one is G measurable. Right, so this random variable needs to be G measurable. The second property, there are two. The second one has a name. This is called the partial averaging property. The partial averaging property holds when what that means is that if I integrate this random variable that I'm interested in, I've denoted by this E of x given G. When I integrate that over sets G with respect to the measure P, I'm going to get the same thing as when I integrate x over those sets in the sigma algebra on which I'm conditioned. So a random variable that has properties 1 and 2, we're going to call a conditional expectation. And this looks quite abstract, and it looks quite different from perhaps how we have seen it before. I mean, when we did the example just before, we didn't have these structures. Often you will see two written as like you're taking and you're integrating respect to P over a set G. So you can write this here as an expectation of an indicator of G times this conditional expectation of x given G. So you'll see stuff like that, and this is being this is being required to be the same. So when I integrate just x over that set. So whether you write 2 like this one, or you write it like that one, this is tomato tomato, it means exactly the same thing. You're integrating with respect to the probability measure, and integrals with respect to the probability measures, we have also denoted them by expectations. So there are some main questions. Existence and uniqueness. Like, does there exist such a random variable? If such a random variable exists, how many are there? Is it unique? And of course, what we've been doing is we've been looking at properties. Like, you can almost guess what the answer to existence and uniqueness must be. The answer is going to be there exists such a thing. And when it comes to uniqueness, it's going to be unique. There exists exactly one such object. I mean, otherwise it would be a poor concept. And then, of course, what kind of properties does it have? Does it have these properties that we already played with up here? Does it have properties of this sort? And of course, yes, it's going to have those properties. Just looking into next week, you're really going to get martingales, just around the corner. This is coming next. As soon as we get this existence and these properties, we can start talking about martingales. And martingale theory, in many, many ways, when you're talking about derivative pricing, this is martingale theory. So martingales, this is a key tool that we're going to be using to do quantitative finance. So what we're going to be doing now over the next, I don't know, half an hour or so is going to be talking about uniqueness and existence. And make no mistake about it, uniqueness, this is not too hard. This is not too hard. Existence, on the other hand, this is hard. And it uses this Radon-Nikodym theory. And this is why we spent all of last lecture talking about Radon-Nikodym derivatives and Radon-Nikodym's theorem. We're going to use those Radon-Nikodym derivatives to create this random variable that has properties 1 and 2. Okay, before I get started on this, I just want to pause and see if there are any questions.
For the second item, partial averaging property.
Yeah.
Is the equal sign there a relabeling, or is it like is it the property?
This is the problem. I mean, this between my fingers now, this is the relabeling of what you have here.
Okay, but the
But this
right
is
hand-
not.
okay.
This is
Those
not.
are-
Right. That conditional expectation you have here, this is not going to be X.
if it doesn't have the partial averaging property.
No. Right. You cannot use X as your conditional expectation, right? Because X is not given to be G measurable. Right? X is F measurable, but F is much bigger than G. So this thing here is not going to be X in general, and you could see that already in our example. When we started computing the conditional expectation of X given Y, this was not X.
Right. But when the partial averaging property holds, it's going to be equal to X. I think that's what it's saying.
It's not.
Oh, it's not saying that?
It's not saying that. It says that when you integrate it, you're going to get the same thing as when you integrate X.
Oh, wait, when you integrate, okay, when you integrate, then it's equal.
But that's very different, right? I integrate two functions just because the two functions integrate to 17. How can you tell me that the two functions are the same?
Okay. Yeah.
Right? You cannot do that. There are lots of functions in principle will give you, I see no, it is not true that the conditional expectation is equal to X in general. When this property here holds, what it says is that whether you integrate X or you integrate the conditional expectation over these sets, you get the same thing. But it does not say that this random variable and that random variable are the same, and this will not be true.
Got it. Okay.
Okay. Yeah, I'm not claiming that this way of defining a conditional expectation is like straightforward. It surely seems quite different from what you had before. Right. The conditional expectation and the original random variable, these two are not in general the same, because the conditional expectation is required to be measurable with respect to a much smaller sigma algebra than X is. Right. You are guaranteed here that X is F measurable. Well, now you're taking a sigma algebra that is potentially much smaller. So just because you know that this is inside F, you're not going to get that this is inside G. You will not have that. So X x itself often fails to be measurable. Okay, so let's do the easy part first, and then let's do the hard part second. When I say easy here, this should not be taken too literally. I'm not claiming that it's just easier than the other one. So so for uniqueness, you take so let y be another random variable satisfying 1 and 2. Okay, so now imagining that I have a conditional expectation and I have another random variable that will satisfy 1 and 2. I want to prove that they're the same. So we're going to show that the probability that y is exactly this conditional expectation, this is equal to 1. Okay, so the proof of this is so you're going to define a set G. You're going to look at that set where, say, y is bigger than the conditional expectation. This here belongs to the sigma algebra G by the first property. Okay. This is a G measurable random variable. This is a G measurable random variable. When we look at the set that one is bigger than the other, that's going to be something inside G. So now that was one. So now we're going to use 2, right? Because 2 says that give me a set in there, then I'm going to have this property. Okay, so by 2, what do we do? We're going to integrate over that set G of y with respect to the measure P. And I know 2 says that this is the same thing as integrating x over that set. And of course, the conditional expectation is going to satisfy 2 as well. So whether I integrate x or I integrate the conditional expectation, this is going to be the same. Oh, good night, guys. Good night.
Okay, come on. Bye-bye. Bye-bye. Come on. Could I shake my hand?
Bye-bye, guys.
At it.
Just saying good night to my kids. So, where were we? We were the first property, right? This is y satisfying 2. The second property, this is a conditional expectation satisfying 2. So I have this string of equalities, and then I can move them. I can now move them over, so I can have here that this is y minus this conditional expectation of x given g. When I integrate with respect to p over g, I'm apparently going to get a 0. So what does that say? What does that say about g? Well, on g, y is bigger than the
Did
conditional
you say G is empty?
No, no, it's not empty. It's a,
The P null set?
yes, these two things are different, right?
Yeah.
Yep. So this implies that P of G and I can do the same. I can do the same thing on the other set. I can look at, likewise, if I looked at G prime to be where Y is less than has P of G prime 0. Right. So they are the same. positive random variable, which on the set, I have a strictly positive random variable on the set G, I integrate, I get 0. That means that there is no mass for G. It's a null set. So this was the uniqueness part, and the existence part is that's the one that is harder, and it's the one that uses this Radon-Nikodym theory. All right, so let me just, before I dive into that proof, let me just recall the Radon-Nikodym theorem from last time. Right, so from last time, right, from last time, we had that if Q is absolutely continuous with respect to P, so remember what that means. That means that P on a set is 0, if that implies that Q on that set is also 0. So if Q is absolutely continuous with respect to P, then there exists a Radon-Nikodym derivative, exists a random variable, which is positive. It has expectation 1. It has expectation 1, and if I'm interested in computing the probability, if I'm interested in computing the probability of A, I can do that by integrating over A of the Radon-Nikodym derivative. Okay, and so what's going to become important for us is the measurability. So we should note here that DQ/P's measurability. Like if P and Q, they are measures on F, DQ/P is F measurable. If P and Q, the probabilities on a smaller one, right, so the absolutely continuous, but now we're looking at them on a smaller sigma algebra. In that case, DQ/P is going to be G measurable. Right, and it's in this latter case, that that we're going to be using the Radon-Nikodym theorem. Are we all familiar with these quantifiers? This means that it exists. There's also a uniqueness component. We don't need that here. This is that there exists a unique random variable, which is not negative, has expectation 1, and when you start integrating it, you can get the Q probabilities out from integrating with respect to the P probability. Again, you can write this here as an expectation 1A, and then it's DQ/P. Right, these two, this notation and that notation. This is tomato, tomato, they means the same thing. Okay, does that all ring a bell from last time? And we have such a theorem, and we looked at a number of examples of these DQ/Ps. Now we're going to use it for a. We're going to use it to prove. We're going to use it to prove the existence of these conditional expectations. Okay, so now we're going to establish So this is the theorem for x integrable. So remember what that means. It means that x is f measurable, and when I compute the integral of the absolute value of x, I'm finite. For x integrable, the conditional expectation exists. So we're also going to have g here is inside f. And exists, and we already saw it was unique. We already saw uniqueness. So there exists this unique random variable. Now we're going to focus on existence, and the way we're going to get existence is using this result we have up here that we talked about last time. So, so the proof, it goes through stages. The first stage is you're going to assume that x is positive. You're going to assume that x is positive. Okay. Then we're going to define. We're going to define a measure PQ. We're going to define a measure Q. Define Q on F by the Lec9 derivative, and the Lec9 derivative we're going to be using is x plus 1 divided by the expectation of x plus 1. So this is strictly positive. So we got ourselves a new measure. We define what its Lec9 derivative is. Right. So remember, what does this here mean? This here is just shorthand notation for saying that Q on a set A, that measure is defined as, this here is just a question of definition, right? So what does it mean when I specify a Lec9 derivative like this? Well, what it means is that if I want to compute what the probability of A is under that new measure, I do that by integrating this x plus 1 divided by its expectation with respect to the measure P. And I do this for any set A and F. So I got myself a new measure. I call it Q. So this was the beginning. So now we consider two additional measures, and they're really not that different, but these ones are defined on this guy, this sigma algebra G, which is strictly smaller than F. And the only thing we do is we just restrict P and Q. Instead of thinking about P and Q being up on the big one, we're thinking about P and Q being on the smaller one. Okay, so we're going to denote them by Q tilde of A. And this is simply just Q of A. But now A is restricted. A is restricted to be inside G. And the same thing with P tilde. This is simply just P restricted to G. Right. P, the original measure, this is something that lives up on F. Q that I got myself created like this, something that lives on F. I take these P and Qs, you just the restrictions. But what I see from this is that because the Radhanucrum derivative is strictly positive, but here I get that, like, we know that this implies that P is equivalent to Q. Like the Radhanucrum derivative being strictly positive means that P is equivalent to Q. It's not just that Q is absolutely continuous with respect to P, it's actually that you get equivalence because the Radhanucrum derivative is strictly positive. Right, so the restrictions are also going to be equivalent. P tilde is equivalent to Q tilde. And so then I can find the Radhanucrum derivative. So this implies that there exists this Radhanucrum derivative. Let me call it Z this time. There exists a Radhanucrum derivative Z. There exists a Z such that this is Radhanucrum theorem. What does this Z here do? Well, there exists a Radhanucrum derivative Z such that, well, one, it's going to be strictly positive. It's going to have expectation under P tilde, which is 1. And it's going to be that when I integrate Q tilde on a set A, I can do that simply by integrating Z with respect to P tilde on that set A, and I can do this for any A and G. Okay, so that's the thing about measurability. This was we should note the measurability properties. If I have measures on F, the Radhanucrum derivative is going to be F measurable. If I have measures that are defined on G, the Radhanucrum derivative is going to be G measurable. So the fourth property here is going to be Z is G measurable. All right, so by Radhanucrum's theorem, I'm going to get a random variable that has a bunch of properties. And one of them is that it's strictly positive. That's because the two measures are equivalent. The next one is going to be that has expectation 1. Okay, that's because Q tilde is a probability measure. That's why we divide by the expectation of x plus 1. This is to make sure that when I take Q here, if I take omega to be A, if I take A to be omega, sorry, then what will I get? I'll just get the expectation, like integral over omega, it'll give me the expectation of x plus 1 divided by the expectation of x plus 1. This is my 1. All right, so this 1 that's coming from here, this is due to the fact that I'm dividing by the expectation of here. The second property is that, the third property is that it's a Radhanucrum derivative, because that means that I get one measure by simply integrating that random variable over sets. And the third property is that this is this G measurability. This was what we were highlighting out here. Okay, so now how can I finish the proof? This random variable Z here, this is going to be my conditional expectation. This thing here is going to be something that looks a lot like the conditional expectation of X given G. But it doesn't look like it, but it will very quickly. I can figure this out. So what is it we have? Well, we have a bunch of properties. Let me start by saying that, well, I have Q of A. Q of A has this formula, and this is for any set A in F. F is bigger than G, so in particular, this formula is true for any set in G. Okay, so that's my starting point. I'll take this formula, and I'll put in sets in G here. So I'll have that this is an integral array of x plus 1 divided by E x plus 1 dp. And of course I can pull the constant outside if I so desire. This is 1 over x plus 1 integral over A x plus 1 dp. So now, we're going to pick a set in G. This is true for any set, even in F. So in particular, it's going to be true for sets that are in a smaller sigma algebra. I know that so this is why I'm using it. I'm having it in G, that Q and Q tilde are the same. When I am in G, and then I'll use the formula that this here is equal to an integral over A of Z dP tilde. And then I'll use again that as soon as I am, like A is in G and Z here is G measurable, then P and P tilde are the same. So this here will become the integral over A of Z dP. Right, so this one here, I'm using that Q is equal to Q tilde on G. Here I'm using property 3. Property T3 on page 8. And here I'm using that A is in G, and I'm using that G ensures that Z is measurable with respect to it. So this is number 4 on page 8. And so now you see we're almost there, right? I combined. I'll move the expectations to the other side. And I'll get the integral of Z dP over A is the same thing as the integral over A of x plus 1 dP. And I'll just move the 1 to the other side and I'm done. This is the same thing as saying that the integral of C expectation of x plus 1 minus 1 dP, this is A x dP. The only thing that remains to check now is, do we have the two defining properties? And, one is it has to be G measurable, and the other one is that it has to integrate correctly. And so we look here, is it G measurable? Well, it's C times the constant minus 1. This here is G measurable. And this equality sign shows that it integrates correctly over sets in G. So this is how to use the Radon-Nikodym theorem to get the conditional expectation. Created these meshes, restriction. So restrict over here, and it allows you to create this random variable Z, and it has all the right properties. It's just linear combination of it, and you get the conditional expectation. So Radon-Nikodym derivatives and conditional expectations, these are highly linked. So therefore, it's also not it should not, when we get into the martingale theory, it should not be a surprise that Radon-Nikodym derivatives and Radon-Nikodym's theorem will play a major role. And the reason for it is that it's all based on these conditional expectations, and these conditional expectations, they ultimately are produced by Radon-Nikodym's theorem. There's no formula anywhere here. It's not like it says that this conditional expectation is equal to that. That's not the case. We don't have a formula for it. It's just abstract existence. And this here was in the case that x is positive. So the general case, when x is a real value, that'll be step number 2. So this is going to be when x goes from omega to r. And we do the usual thing. We split. you write x as x plus minus x minus, and then because the absolute value of x is finite, you'll get that the absolute value, you have to put a plus here, and this will be the expectation of x plus the expectation of x minus. Right, so each one of those will be finite, and then you can use, so by the first step, we'll have conditional expectation of x plus given g, as well as the expectation of x minus given g. These two guys, they exist. We'll have that. Okay, so then if I take the expectation of x given g, I simply just take the difference. Take the difference, that's going to satisfy. And then this guy satisfies 1 and 2. So the second step here, this is much more, this is much simpler because we did all the hard work in the first one. We just split it into the positive part and the negative part. This is something we've done a number of times. You make sure that the absolute value is nice, then the positive part and the negative part, each one of them will inherit the properties coming from the absolute value. And then given that these two are well defined, you can take the difference, and the difference is going to be the thing that does it. So this is the existence. There is such an object. There is a conditional expectation as soon as x is integral. There's no formula. There's no way to compute it, and so this can be tricky to work with. And as we have talked about already, like this abstract conditional expectation, it has to satisfy properties that you're familiar with. So what does it mean to satisfy properties that you're familiar with? Well, if you look at some of the exercises over here in the end of the textbook, if you look at something like exercise 210, you've probably seen conditional expectations of this form, like you take y given x. And the way that you've probably seen how to compute such an expectation is by taking a joint density and you divide out by the marginal, and you get this conditional density. Right, so you have seen a formula for the conditional expectation when you have a joint density, right? So there should be a connection between what we just established the existence of, and then what you've seen in an earlier probability class. But it's pretty far away, right? We have this abstract existence that's coming in through Radon-Nikodym's theorem. That object we are working with, why would that be exactly what you've seen in the earlier probability class? Under the assumption that there's a joint density. This is something that has to be proven, that these two things, they are consistent. And so this exercise here, 210, it takes you through the steps that you have to do, and then you end up concluding exactly that, yeah, it works. This is really the same quantity. This is the same conditional expectation when you have a joint density and you're defining it the way that you did in an earlier probability class. The point, of course, being that now we're using measured integration theory, and this is more abstract and it's more general, and it will not rely on having a joint density. Indeed, the only thing that this theory relies on up to this point is that the Lebesgue integral exists and is finite. Okay, are there any questions or comments about what we've done here? Otherwise, the next thing to do is to look at some properties. questions or comments? I'll spend the last few minutes listing properties that this object here has. So properties. Again, if you go into our textbook, there is a laundry list. There's a laundry list of properties of conditional expectation. We just guide you through where you can find it. So this is over in. See, he starts here. He starts here in a theorem, and it's a pretty long laundry list. It really does go through a number of things, and he outlines the proofs and so on. So you can find a lot more information about the properties that we're going to be discussing now. I'm saying this because one of you asked in the beginning of today's lecture if this is a good source for supplementary material. So this is the best source. Steve Shreve, for those of you that don't know him, he just turned 70. And he's been doing this all his life. And these were like, these books here, you've been on their way for a number of years at Carnegie Mellon, and he's been using them to teach for the master's program, and I use them to teach undergraduate versions of these master courses, which is what we're seeing now. I've been using them for years. I don't think there is any better material you can find out there. This is an excellent source. There's a lot more material in here than what we have time to talk about in class, but this is as good as it gets. Okay, so some properties of this conditional expectation. So one is that it's linear. Okay, that's good. Second one is that if y is already G measurable, and I need x times y to be integrable, and then when I compute the conditional expectation of x times y given G, I'm trying to estimate x here, but I already know what y is. I'm trying to estimate x, I already know what y is. Okay, so I can put the y outside. So that's there. There's something that is often referred to as iterated expectations. So what you do is you take a string, you take H inside G, inside F. Right, so now we have three sigma algebras. So we have, as before, G inside F, but you also have H. And so if you take the conditional expectation of X given G, this is going to give you a G measurable random variable, and then you condition on H. So you iterate. So now you're going to end up having two sigma algebras next to each other. And the thing that wins is H. The smallest wins. This actually has quite interesting implications. So the smallest sigma algebra that has ever existed is, of course, the one that just has omega and the empty set, when there's no information at all available. So this implies that if I take this one, so for him, we get the expectation, right? I'm conditioned on nothing. So I'm just going to get the expectation of X given G. That expectation, so the expectation of the conditional expectation, this is equal to, well, just the expectation. when I had office hours earlier today, this here is this has a name. This means that the conditional expectation of x given g is an unbiased estimator of x. There are some students in this class that have seen estimators before, and some estimators are biased and some of them are unbiased. The unbiased ones are the ones that are correct on average. So if you're thinking about the expectation of x given g as an estimate of x, well, if you want to be unbiased, it has to be correct on average. And so it is. The last property, and then we'll call it quits for tonight, is the last property we'll use, we'll list tonight, is that if I take, indeed, if x is independent of g, so what would that mean? That means i.e., what does it mean for a random variable to be independent of a sigma algebra? It just means that x is independent of the indicator for g, for any g inside this bigger sigma algebra. Right. That's not a random variable, right? So we don't really know what that means, but 1g is a random variable. So what we're saying is that you take any set inside the sigma algebra, when I look at the indicator for that set, that's a random variable and it's going to be independent of x. So if we have that, then the conditional expectation of x given g, now there's no connection between the two. I'm just going to get the unconditional one. And that was one of the properties that we had used earlier on. So for example, so this implies that if g is equal to sigma y, well then the conditional expectation, then when x is independent of y, the conditional expectation of x given y, this is exactly the unconditional one, which is one of the properties that we had used in the example in the beginning of the class. Okay, I think my clock is 8 o'clock. Are there any comments about conditional expectations that we had today? So next time we're going to be talking more about conditional expectations, but at this point you will have enough. You have enough material to try to attack the homework. Are there any questions or comments? So I know based on past experience that when we reach this point in the course, the material can start seeming very challenging. This is pretty abstract. Okay. So
I have a question.
Yeah.
When you proved property 2 in the existence part,
Yeah.
why did we choose to break x up into positive and negative part to show that it existed? You said like we did the hard work in problem 1.
Yeah, because what this splitting up, we have seen that before, right? That's not this is not a new trick. But the hard part was happening here when x is positive, right?
Okay.
We need x positive, right? Otherwise, this is not going to be strictly positive. If x is taking real values here, if it's Gaussian or whatever value, it can be negative, right? We're not guaranteed that this thing here is positive.
Oh, so that's why you want to do the plus and negative part. Because
if I have a general random variable, I can't do this.
I understand now, because it might be negative.
Because it might be negative, and then this will not be a probability measure, right? If if I'm looking at this formula, you think about x as being Gaussian, right? Then q on a set could be negative, and this would not work. That would not be a probability measure.
Okay, so that's why that trick avoids that. Okay, I understand.
Yes, that's right. So then we go to this splitting up, right? I split it up into the positive part and negative part. X plus is positive, right? And x minus is positive. Right? So then I can apply step 1 to both of these random variables. And then I'll just look at the difference, and it's going to give me the thing that I need.
Oh, okay. Yeah. That makes sense. Property 2.
Like in this random variable we have up here, I cannot just feed him into the formula. This would not work, because it will give me a Q measure that can take negative values, and so that will not be a probability measure.
Okay. So the first part was proving that it was G measurable.
Well, the first part was to say, give me a random variable that's positive.
Mhm.
Can I define the conditional? Can I guarantee that the conditional expectation of a positive random variable exists?
Okay, and then the first part was constructing this expectation to be.
Yes. I mean, we have in the definition of a conditional expectation, there are properties that have to be met. We're saying that a random variable satisfying 1 and 2 is a conditional expectation. But who says there is such a random variable?
Okay.
Right?
Yeah.
Why would, I mean, I list a bunch of properties and I say, okay, so if there's a thing that satisfies properties 1, 2, 3, 4, and 5, I'm going to call it Casper's variable. Okay, and then we develop a theory for Casper variables. But I mean, this might be the empty set. We need to make sure that we have such a thing. And so that's why we're going through this proof.
Okay, I got you. The reason I got confused was because we showed this partial averaging property in like the other page, and
Yes.
then like 2 was like labeled the partial averaging property. So
Yes. Yep. Yeah, this long calculation here goes to show that you have the partial averaging property. This here is the partial averaging property, right?
yeah, but on the next page it was like labeled 2 if you look.
But, okay, but so then
That's what I got.
1, this is like step A, and then
now step B. Okay. Yeah. I was like, wait, we're not proving.
No. I'm just breaking the proof up into 2 parts. Sorry. Now I understand.
All right. Good night, Professor. Thank you.
Okay, have a good night. Are there more questions before we hang up here? We just want to make sure everybody has had a chance. Okay, if there are no more questions, then I want to remind you guys that we have office hours tomorrow morning. And again, the homework has been pushed a few days, so you have a little bit more time to get it done. Otherwise, I'll see you guys on Tuesday. Have a good night.
Bye.
Bye-bye. There's the problem.